All right. I want to continue from last time, of course, working on the problem of the divisibility properties of this, the sum of orders of the cyclic group. And one thing I found interesting is that sort of the difference between the actual writing down of mathematics, or in this case, sort of the notes I'm doing now with these videos, and how I'm thinking of mathematics, sort of just in my head. And I noticed quite a big difference between the. I get to focus way more on the details, of course, as I'm writing things out now, and also trying to semi-explain them at least as I go along. So it's a very good moment to really focus on the details that are unclear, and I'll notice there's still a lot of things that are unclear as I'm explaining these things, so that's very good. But then really coming up with new ideas, I notice that really goes, it's more natural to do sort of in if I'm just thinking by myself, which I guess is not too surprising. That being said, today I want to highlight some new ideas that I've had for understanding this problem better. All right, let's get started. So let's see, where were we last time? All right, so this was a little bit silly, of course. If the idea is that we're looking at you know, the group of invertible elements, which are, at least for sorry, we're looking at the cyclic group of order n, and then we look, or better said, we're thinking of the ring of integers modulo some n, or in this case q, so zq. And we look at the invertible elements, and if q is a prime, then that really gives us a group that's isomorphic to the cyclic group. That's a result from Gauss, I believe. And that was sort of the key property that I used here, right? We had here a to the power 3 equals 1. So we can really think of this as, since this is a cyclic group, we can really think of this as, oh, we have we have some element, let's say x, and then in zq minus 1. And then when we multiply this by 3, we want to get back 1. Let's see. Yeah, and of course that depends on the divisibility properties of q minus 1, and that was sort of the key step that we had here. And that's what I want to focus on today a little bit more. So you know, we got here that this is only possible if there exists such an element. And I think last time I also noticed I showed that, okay, we're looking at solutions to this, or better said, sorry, solutions to this that are non-trivial in the sense that we don't allow a here to be like 1. Right, that's because we're dividing by p plus 1. And again, we're doing this trick that instead of focusing on p, we want to look at minus p, because then we get a sort of nicer expression. We get this geometric series instead of this geometric series with like a negative scaling factor, and that just makes life a little bit simpler. Okay, let's see. So what do I want to do? I have the following. I know that for a given pk, if I calculate s of pk, I get out p to the power 2 plus 2k plus 1 plus 1 divided by p plus 1. Yes. Now, if I look at S of p k, mod. Sorry, if I want that S of p k divides some q sub, let's choose L. And just to be clear, I'm not imposing any conditions at all on q and p. They are arbitrary now. But if I want this to hold, then what this means is that following the above, that right, I'm not doing anything anything fancy here. And of course that this equals 0. Let me fix this notation. This is terrible. This is 0. Okay. So now I can let's phrase this again a little bit more mathematically. If I look at the integers modulo q to the power L, I just get these guys, which form a ring. Okay, what do we know? We know that. Well, let's look at the numerator. We want that this holds. Is that this is 0 mod ql, mod to the power q to the power L. So for this to hold, we require that this holds, but we exclude the case where p is -1 itself. And you can sort of think of this as a trivial solution to this guy, right? If I plug in p -1, then of course, since this part here is odd, that doesn't matter. That sort of factors out. Okay, now what I'm going to do is I'm going to define a map. F, which just takes me from ZQL to, to ZQ to power L again. And what it does is the following. It takes some element A and maps it to Q to power L minus A, or better said, okay, so really we can think of this as the, this is just the inverse map when we think of Z to the power QL, sorry, Z sub Q to the power L as an additive group. Okay, and why is this nice? Because, well, first of all, we know that this is a bijection. This is to see from the fact that this is a group and inverses are unique. So that is nice. And the idea is that if I have a solution to this equation here, that's the same thing as having a solution to and maybe to make that clear, the reason is I can just take, if I have some solution P, if I then send it to minus P, and I plug that in here, right? So let's say minus P is then a value we plug in here, then it'll, we get exactly the same thing. And that was sort of the trick that I used here, although now a little bit more advanced. Okay, so now what this tells me is that this is sort of nice because I can now look at the solutions to this, which we can sort of think of as the as roots of unity of order 2k plus 1. And in particular, one thing we can do is this equation tells us that, we're raising something to the power and we get a 1 at a certain point. That in particular tells us that our p needs to be invertible. Okay. Or it needs to be invertible under multiplication in the ring ZQL. And let's see. In fact, that imposes quite some strong constraints, and I guess we can count the number of solutions, and maybe also use that to get a handle on these equations better. Okay, so let's see. So let me put here except p is 1. Right, that's sort of the trivial solution that we were throwing away by including this denominator. Okay. Okay, so what else do we need to know? We need to have that p mod q to the power L is invertible. That was the above argument that I had. And that is already quite nice because this simplifies life a bit. Let's see. I see. Now, what we used in the previous argument is that, we just had L equals 1 and K equals to 1. Was that ZQ and the invertible elements, that's isomorphic to ZQ minus 1. And so we knew the order of this group, and that allows us then to really restrict the sort of roots of unity that we can have. And so I will do something similar now in this case. Now, I do believe that we just get this, right? So if we now look at the invertible elements, we again get a cyclic group. And it's the same size because everything is invertible except for 0. And now, as I'm saying that, I realize that doesn't make sense because there's a lot more non-invertible elements in Z sub q to the power L minus 1. Okay, so what should probably happen here is that we get the I believe this is the Euler-Totient function, which tells you the number of elements that are invertible in this ring. Let me double check that statement. And let me share my screen here, because why not? All right, so I thought this was, let's see, I thought this was discussed in some work from Gauss, like Gaussian interpretation. Yes, this was the paper I was looking for. Let's see, invertible elements in Zn. Okay, there we go. Remember that there was like a separate Wikipedia page. Just a group of units, mod n. That was maybe the term. There we go. Okay. Okay, so that checks out, right? We see here the Euler-Totient function. So I remember in the general case, yes, okay. Yeah, so here this is the statement. And here, of course, I'm making explicit use of the fact that q to the power L is, of course, a prime power. And this tells you that this problem becomes quite a lot more complicated as soon as you start looking at um, let's see, you cannot really use um, right, you cannot really just use the fact, oh, we get a cyclic group if you start looking at mod n, where n is not a prime power. But let's keep life simple and let's restrict to these cases, because okay, there we know it's cyclic, and we don't have to know too much about the group structure. Let me have a quick look if there is anything known, like for more general cases. It seems like a problem that should have like a nice structure to it. But I remember that that was sort of not the case. I had like a list here somewhere. Okay, yeah, this looks kind of weird, I guess. Okay, this that seems very complicated. It does seem we always get like a okay, yeah, we get of course a product of cyclic groups, which makes sense, right? These are abelian groups necessarily, since we're doing a multiplication mod n. So it makes sense that we get a tensor product, or sorry, just a product of cyclic groups. It's just a fundamental theorem of abelian groups for the finite case, of course. Okay, let's go back to the notes. Let's see. I should stop sharing here. Okay. Okay, let's write this out. This is for q prime power. Okay, so we could be a little bit more general and consider here 2 times q to the power L, but um, oh, that might be useful to tighten some lower bounds, but let's not use that for now. Okay, let's see. Um, this should be I don't really like this. Let me rewrite this as like this. Maybe not necessarily very nice here, but whatever. Okay. Now what we want to do is, okay, we know that this group is cyclic and of this order. Let's see. Hmm. So what I want us to do is that we have this. Yes. Okay. Um, okay. Yes, we have this, and now the question is, we're asking the question. Okay. Does there exist an element 3 times um, 3 times some k? Oh, sorry. That's stupid notation. We have 2k plus 1. That's the exponent that we have here. And then now, since we know we have the structure of a cyclic group, we can phrase everything just in terms of the integers modulo modulo q to the power l minus q to the power l minus 1. And so we can phrase that really in terms of multiple. Let's see. Okay. Let's be very careful, because this is something that has been confusing me as well a little bit. We have some element of this form. I want this to be 1 modulo q l minus just modulo q to the power l. Okay, then we say we can translate this by interpreting by saying, oh, this implies that P needs to be an invertible element. And so we can suffice us to solve this purely in terms of the group of invertible elements, which we know is cyclic. So what does this mean in cyclic terms? It means, okay, in my group, I want to get out a 0 element. So I'm going to represent my group element as a G sub P. I see. Yeah. Okay. Okay. Yes, my issue was that I wanted to think of these as the integers modulo n. But here, this exponent, is repeated application. Says, okay, apply p and multiply with p, multiply with p. Now, the multiplication in sort of if we look at the group of invertible elements, it becomes addition. Right, that's going to make our life simpler. But so this exponent means, oh, take some element g sub p and apply it again, and another time, or in total repeat it 2k plus 1 times. And so I was a little bit concerned about this, because when I write something like this, I was like, oh, that doesn't make sense. But when we have a abelian group, we can, consider sort of I guess they call it ZG, or maybe this also works for non-commutative groups. But let's say with commutative groups, and there's like a way to think of this as some kind of module, I believe. But for abelian groups, we can just specify how many times we apply an element, and that I think at least formally that is completely fine. So now I should be able to interpret really as an equation in this form. So this is definitely, I need to double check these details, because this is yeah, not that obvious to me. Now let's see. Now we look here, and now what we see is we want that 2k plus 1 is a 0 divisor modulo some n, but we know that let's see. my initial statement that I want to make is that we should have that 2k plus 1 divides q to the power L minus q to the power L minus 1. But I'm not sure if that's actually true. Let's see. The statement that we want to have is that I'm just worried that we might need to look at the if there's any factors in common or something like that. Let me be lazy and just check this real quick online. Divisor mod n. Yes, okay. This was indeed correct, what I said. We have that 2k plus 1 is a zero divisor. And to be clear, this should be a zero divisor that is sort of not zero itself. Depending on convention, that might be different. Okay, so 2k plus 1 is a zero divisor. That's the same thing. Well, let me be clear here. It's a zero divisor of this guy here, if and only if the GCD. Right, so if they have any non-trivial common factors. Okay, and now I guess this was also one thing I got hung up last time. I'm not really sure why this is necessary, but anyway. Oh, let's see. There's actually a claim here, although they haven't. Sorry, I'm reading the post now, and I say this is a question, not a statement. Okay, that indeed seems to be the case. Okay, so let's go back and do some writing to see what we can do with this. Okay, so what does this statement mean? And to be clear, we are excluding here we are really excluding here the fact that we get out we're sort of really excluding the case of a zero divisor that is zero, because we were dividing by p minus 1, and when we translate that back into the in the cyclic group picture, then that exactly works out. And sort of the reason C is that we want to have p to the power 2k plus 1 equals 1, but 1, when we view that instead when we viewed it as sort of an multiplicative picture, it's the identity. So then when we take it back to the cyclic group picture, it's really just the zero. So there's a lot of different groups sort of flying around that are easy. I've gotten very confused with them actually thinking about them. Yes. Okay. Anyway. Okay. So this is false here. Now we want that. Okay. So what does this imply? This implies that s of p to the power k okay, does not divide. Sorry, that's silly. Q to the power L does not divide Does not divide S of P to, okay. Okay, sorry, that's not the right order. If 2k plus 1, no, actually, the statement here. If the GCD this guy and this guy and this guy is greater than 1, oh, that's annoying. Of course. Oh, this is becoming messy. Let me just start from scratch here. This is just a mess. So if we see that the GCD between these two quantities is greater than 1, then we know that then we know that Q to the power L does not divide S of P to the power K. And the previous statement was just a specific instance of that, where we had K is 1 and L is 1. And there we had this very nice form, because what did this reduce to? This reduced back to all the GCD of 3 and Q minus 1 is greater than. Wait. Let's see. Am I saying that correctly? No, we don't want to have 0 divisors. So when this is equal to 1, if this is equal to 1, wow, my bad, right? Because we see that here the GCD, I mean, if Q is 1 modulo 3, then the GCD is clearly not 1, right? Because we have 3 here and we have something that's divisible by 3 here, so the GCD is at least, well, it is 3, because 3 itself is prime, of course. Yes. And of course, if Q is 2 modulo 3, then well, let's see. Let's make that argument clear. We have a prime, and then we have something that is not divisible by that prime. Yeah. So since the prime is only divisible by itself and by 1, then we're good. Okay. So okay, let's maybe phrase this even more abstractly. If I plug in Sn, let's see. Okay, what my input is some general n. Which I can rewrite as in its prime factorization, something like this. Okay, and then since we know that S is multiplicative, we get out the following. Oh, I should have, let me use P here to be sort of consistent, and K here. By the way, one thing I realized is that the multiplicative property of Sn really derives from the Chinese remainder theorem. Why is that? Well, we're asking a question about the order of a group element. which is just a question that is that it as a two rings that are the same. Sorry, if I have an isomorphism between rings, then the uh, the function that calculates the order of a given group element sort of commutes, right? It doesn't matter where I calculate it. And so the Chinese remainder tells us, okay, it suffices to do the calculation um, in z. Sorry, what I want to say is the following, right? We have some zn, and then we know that this is isomorphic to z, and let me try to use the same notation. I'm writing here a sum. Should be a sum. Let me double check this. Yeah, that should be definitely a sum. No, it's not a sum. Silly. Very silly. It's just these are just ring products. Dot dot dot. Yeah, so calculating the order sort of nicely factors through. I do realize I need to make that argument a little bit more concrete, but I'll do that some other time. And I think this is also sort of, I guess, morally the reason why a lot of sequences that you encounter in practice are multiplicative, just because they sort of nicely factor through this this isomorphism. Okay, where were we? We're here. Okay, we can play the same trick as before. So let's go here, right? We let's see. Okay, okay, okay. Okay, so let me just expand this. Oh, okay, this definitely becomes a lot more messy when you have now like a product as we do here, so just a single term. Because why? Well, the statement that we want to have is that this is so I guess one thing that I can do is let's see. So I want to put this here. And what I'm pretty sure is that this is equivalent. Yeah, I don't see anything going wrong with this. It does seem quite powerful, so I want to double check that. I just take the exact same term as before. And I want this to be 0 mod p j k j. Yeah, this product makes things a lot harder. A lot harder. Um, because what does this tell you? This tells you that there's at least, let's see, this tells you that there's at least one I such that um, PI, the GCD of PI. Wait. We want to have here such that there's at least one I such that GCD of 2k plus 2ki plus 1. Um, okay, actually, let's stick here with just n. Just n. There's at least one. Okay, so if all all so just trying to see how this works with the this initial proof that we had when we looked at these square-free integers. And there we require that there is at least one quantity such this holds, but that we want to show that this property didn't hold. So I'm just confused about that. Let me just write this down. If all okay, I'll need to think about this more some other time because I need to go now.